Here I know that lambda is equal to dq over dx. Therefore, d big Q is equal to lambda dx. So I'm going to plug that in here. K is a constant, pull that one out. Little q is a constant, pull that one out. So then I'm left with lambda dq, big Q, over r squared sine theta.
Memory lambda dx.
Yes, it is. Thank you very much. And I appreciate you letting me know now. All right. Lambda's constant, so I can pull that out front. And R is this right here. This distance from here to here is big R. I basically have a right triangle. I have big R, little r as the hypotenuse. That's a right angle. And this is x. So I have a relationship between x and r. And r. I know that x squared plus big R squared equals little r squared. So I can stick that on the bottom. Sine of theta is the opposite over the hypotenuse, so that's big R over little r. And that is really a hideous right triangle there. And so if I make those substitutions, pulling lambda out, I get k lambda q j hat integral dx over r squared, which is x squared plus big R squared, times the sine of theta, which is big R over little r. So I just got rid of r, but now I've brought r back in, so I've got to deal with that. So I got k lambda q j hat dx. Oh, I got a big R here I can bring out. R is just the square root of this. And so in the denominator, I have x squared plus big R squared to the 3 halves. We can go slightly differently here. If we did this, if I'd done the sine substitution first, I would have ended up with lambda dx big R over r cubed. R squared is equal to that, and so it just ends up being r cubed would be x squared plus big R squared to the 3 halves. I now have a single variable here. It's time to throw in the limits of integration. What is the largest and smallest values of x? Or with proper grammar, what are the largest and smallest values of x? I guess I need to state something here. Uniform charge distribution along infinite line.
0 to infinity. 0 to infinity.
There's a slightly simpler way of doing it. If you do 0 to infinity, you're just looking at that part of the line.
Oh, negative infinity to infinity.
Yeah. So now it's just a simple little calculus problem of, just look at the calculus piece of it. Integral of dx over x squared plus r squared to the 3 halves. Which of course is all right, there's 2 approaches to doing this. In math class, how would you do it? What's the approach you would take?
Probably some sort of substitution.
Yeah, what kind of substitution?
U.
What would you use for u?
What's in that,
The x squared plus r squared?
yes, sir?
If we did the u substitution. Sorry, I might have just cut you off. That is what you were saying,
Yeah,
right?
yeah, yeah.
Okay.
You good, you good.
So what is du then?
Just 2x.
There's more.
Plus 1.
No, no. No, that's a constant, that derivative, that the zero dx. I need to have an even number of differentials there. So if I plugged in, so dx would be 1 over 2x du. So if I plug that in, I'm gonna have a mess on my hands. I got something nice in the denominator. I'll have u to the 3/2 in the denominator, but I got an extra x here, which is square root of u minus r squared. U substitution, not the easiest way of doing it, if it's even possible.
Is there a trig substitution?
Yeah. I'm not gonna do it this way, I'm just gonna set it up, what you're doing, and then I'm gonna show you a simpler way of doing it. So if you let x equal, I think it's tangent, r
Yeah.
tan u. Because then you'll end up with a tan squared plus 1, which is, I think, secant squared, and then you go about it that way. If you got the time, I actually gave a problem similar to this on a test. I had one student do the trig substitution method. Of the students who got it right, I had one student do the trig substitution method and work the whole thing through. It was impressive. There was a simpler way of doing it, which the other people who got it right did. Some people just looked at it and went, But the simplest way, and it's simpler on quizzes and tests because it's written right there. There we go. The physics way of solving this is you look it up. What you would look up, what's at the top of the quizzes and tests, is integral of dx over a squared plus x squared to the 3/2 equals x over a squared square root of a squared plus x squared. That is given. I will give it to you. It's already been done. This is not math class. If you got a shorter way of doing it, take it. If you are working at home and you're thinking, I can't find the old test to find this equation, go to table of integrals. If you go to Google, type, or whatever your search engine is, type in table of integrals, it'll be on there. Unless you got table of integrals for middle school students, and I'm betting you don't. So what that says is when I'm doing this integral here, the r, I have r instead of a. So I end up with the integral, I end up with x over big R squared, square root of r squared plus x squared from negative infinity to infinity. And so now, well, still looking at just the integral piece of it. It's not going to be 0. We do need to bring those constants back. Well, the r squared is a constant. It's just going to pop out. So I end up with r k lambda q j hat over r squared times that. So if I plug infinity in, what do I get?
Infinity over infinity.
Which is?
One.
Good enough. 1 minus, if I plug negative infinity in, what do I get?
1. infinity over infinity?
which is
I have no idea.
Negative infinity over infinity is -1.
-1.
Okay.
Thought it was negative over negative.
Yeah, this is squared, so whatever.
Oh, gotcha. 'Cause it would-
Remember, when we're talking about infinities, I think you can easily make an argument infinity is not really a number. It's just something huge. So if x is huge, r becomes insignificant here. And so we have whatever x is squared, so it makes that a positive square root of it. My denominator is positive no matter what, unless we're dealing in an imaginary space, which we're not. The numerator is whatever x is, so it's positive or it's negative, depending upon which limit we're taking. So we get 1 minus -1 or 2. So I end up with 2k lambda q over r j hat. That is the force acting on some charge, little q here, a distance big R away from an infinite line of charge that's a uniform distribution. I can't simplify it really much more than that. There's another way of doing it that I'm going to put an alternate form of it up here. But j hat is just away from the line. So if I reorient the line so it's vertical, the force, assuming everything's that the charge distribution or charge density and little q are the same sign, it just means away from the line. If they're opposite signs, it'll be towards the line. Questions about this before I show an alternate form? What is K?
Coulomb's constant.
Okay. Sometimes a little e down there, sometimes with a c down there, depends on my mood, and apparently sometimes with no subscript. That's equal to 1 over 4 pi epsilon sub naught, where epsilon sub naught's permittivity of space, free space. So if I make that substitution, I'll stick it over here, we end up with 2 lambda q j hat over 4 pi epsilon sub naught, big R, which becomes lambda q j hat over 2 pi epsilon sub naught R. And the reason I present this form to it is that later on it'll be convenient to be working in terms of permittivity instead of Coulomb's constant. You shall see this again. And I know if I watch this video again later, I'm gonna be really disappointed, because in my head, I was almost dead on James Earl Jones. But yeah, I'm just gonna be sadly disappointed, so I can never watch that. Questions? As we're about to do infinite sheet of uniform charge. All right, infinite sheet. Surface charge density. So this is jaunty tilt view. Side view. distance right there. Oh, what the heck, we'll stick with big R. If you need more of a visual, imagine this is, actually, let's take the wall. The wall has uniform surface charge density on it, and I want to figure out what is the charge, what is the force on a charge, let's say at the camera lens. The center of the camera lens, if there's a charge there of little q, so let's throw a little q into it. A little q there, little q. What is the charge on that? Assuming this wall is infinitely large. So controversial, people are walking out. Sorry. No. Hey, let's do what we've always been doing. Let's find some differential of charge and find the force between it. So, I'm going to take a circle of charge here and of radius x. And the distance from the circle of charge to here is little r. So I've got some ring of charge. This distance here is little r, and this distance here, x, y, whatever letter you want to use that we're not already using. So if I think about it, I've got this ring of charge that is of charge dq. Let's first, so this has some charge d big Q. And the symmetry argument again. If I'm looking at it from this point of view, the only thing that's going to survive is that which is coming perpendicular to the sheet of charge. Anything else, for every charge here, I've got a charge here that's going to cancel out all of the vertical components the way I have it drawn. The vertical components all cancel out. Only thing left is the horizontal component. So by symmetry, we've reduced our problem in half already. And so the force that I care about is, oh, what the heck, I hat, J hat. I hat, I do need an angle in here. I want to make this angle, actually just to keep in sync with the notes. Yep, just that angle. Theta. So I hat K times charge 1 times charge 2 over the distance between them squared. And again, I want to care about just the horizontal component, so times the cosine of theta. And again, there is a j component piece, which we will do away with shortly. Conveniently, it's an infinite sheet. Being an infinite sheet, that means I can assume that the point that is closest, the point on the sheet that's closest to the charge is the middle. Integrate. This goes off to 0 by symmetry. And so we're left with just this. It is the same process as we did before. We have 3 variables here, big Q, little r, and theta. We need to get them in terms of a single variable, then do our limits of integration, then solve, and then simplify where we can. We pull out the constants, so I got I hat, K, little q, and that's it for now. Cosine of theta is the adjacent over the hypotenuse. So this right here is big R over little r. So I got a big R popping out here, and then I've got dq over rq. And quick check, just to make sure I didn't do something stupid, because I did 2 steps at once. So I got big R over little r, big R comes out, little r times r squared is r cubed. I'm good with that. The k and the q and the I go out also. All right, I'm feeling relatively confident that I haven't messed up. dq, we're gonna take advantage of our charge density. Sigma is the surface charge density, which would be dq over dA. Linear is dq over d length. Volume is dq over dv. So dq is equal to sigma dA. So what is the area of that circle of infinitely thin circle of charge? Just the thin circle of charge, not the area of the circle, but of that ring of charge.
Two pi x.
That's one dimensional. You're missing one thing. It's gotta be 2 dimensional.
2 pi y.
I went with x this time instead of y, but that would get you to the same place. All right, here 2 clues why something is off on just saying 2 pi x. That's a differential, that's not. If this is infinitesimally small, this better have an infinitesimally small piece to it.
Dx.
Yes. This infinitesimally thin ring still has a thickness to it.